This battery doesn't last a day or a year. Some of them keep working for 50, 70 or even 100 years without ever needing a recharge. They already exist. They've been operating silently for decades, and almost no one uses them. This isn't science fiction, it's atomic battery technology, one of the most reliable power sources ever built. Atomic batteries are older than modern computers. Their story begins in the early 20th century, when scientists first realized that radioactive decay was not random chaos, but a predictable physical process. In 1913, physicist Henry Moseley demonstrated that atomic behavior followed strict numerical laws. For the first time, energy realized from radioactive elements could be measured, predicted, and engineered. A few decades later, a new question emerged. If radioactive decay is predictable, could it be used as a power source? By the 1950s, during the early Cold War, that question moved from theory into engineering. And this is the first important takeaway. Atomic batteries weren't invented to be impressive. They were invented to be unavoidable, when no other power source could survive. First Voyager launched in 1977. Nearly half a century later, it's still sending scientific data back to Earth from beyond the edge of the solar system. At launch, its power system generated roughly 470 watts of electricity. That output has been declining slowly and predictably for decades, exactly as physics predicted. Solar panels stopped working billions of kilometers ago. The atomic power system didn't. In deep space, where maintenance is impossible and failure is permanent, this kind of reliability isn't impressive, it's essential. The transition from theory to engineering happened in the 1950s. At Oak Ridge National Laboratory under the United States Atomic Energy Commission, engineers began developing the first radioisotope power sources. These systems were never meant to be efficient, they were meant to be autonomous. One of the key scientific breakthroughs came from Paul Rappaport, who formally described betavoltaic energy conversion, the direct transformation of beta radiation into electrical current inside a semiconductor. There was no single inventor. Atomic batteries emerged at the intersection of nuclear physics, semiconductor science, and Cold War engineering. The goal was simple: build systems that could survive without humans. At this point, an important clarification is needed. When we say atomic battery, we're actually talking about two very different technologies, and they are often confused. Understanding this difference explains almost everything that follows. Radioisotope thermoelectric generators, or RTGs, convert heat from radioactive decay into electricity. Hot on one side, cold on the other. That's why RTGs can produce tens or even hundreds of watts, enough to power spacecraft instruments, heaters, and transmitters. But that power comes at a cost. RTGs are large. They run hot, using plutonium-238 as their heat source, the isotope commonly used in space RTGs aboard missions, like Voyager, Cassini, Curiosity, and Perseverance. Inside the generator, temperatures can exceed 1000 Celsius, while the outer surfaces typically operate around 500–600 Celsius. Betavoltaic batteries, by contrast, operate at near ambient temperatures. Size matters too. A typical betavoltaic battery can be smaller than a coin, sometimes closer to a grain of rice. RTGs, by contrast, are measured in tens of kilograms, with shielding, heatsinks and radiators. The trade-off is power. Betavoltaic systems produce microwatts, not watts. RTGs are built for power in extreme environments. Betavoltaics are built for time. Once you see this distinction, the rest of the story becomes much easier to understand. Power versus time – that's the entire trade-off. The lifespan of an atomic battery depends on two things: the radioisotope and the semiconductor material. In betavoltaic systems, common isotopes include nickel-63 with a half-life of about 100 years and tritium with a half-life of 12.3 years. But the isotope was never the main limitation. Early designs used silicon as the semiconductor. Under constant beta radiation, silicon slowly degraded. Each high-energy particle creates defects in the crystal lattice, atomic-scale damage that accumulates over time. After years of exposure, efficiency dropped by tens of percent, even though the radioactive source itself was still stable. This is where early designs quietly failed, not because of nuclear physics, but because solid-state physics wasn't ready yet. That changed in the late 20th century. Materials like silicon carbide and synthetic diamond can tolerate radiation doses orders of magnitude higher than silicon, while maintaining electrical performance for decades. Synthetic diamond proved especially important. It is radiation-resistant, thermally stable, and has a wide band gap that supports leakage currents even after long-term irradiation. You don't need to remember the materials. What matters is this shift. Atomic batteries don't age like chemistry, they age like physics. Staying radioisotopes naturally emit beta particles as they decay. In practice, only a few have ever been suitable for betavoltaic batteries. Tritium was one of the earliest choices. It emits very low-energy beta particles, which makes shielding relatively simple and safe. Typical betavoltaic tritium cells produce tens to hundreds of microwatts, but its half-life is only 12.3 years. Meaning power output drops noticeably within a few decades. Nickel-63 became a more attractive option later. Its beta particles are still low energy, but its half-life is about 100 years. The trade-off is power. Most nickel-63 betavoltaic batteries operate in the range of a few microwatts to a few dozen microwatts, delivering far less instantaneous energy, but doing so consistently for multiple generations. Promethium-147 was also explored in early research. It offers higher beta energy and can reach hundreds of microwatts or more, but at the cost of stronger radiation, heavier shielding, and a short half-life of about 2.6 years, which makes it unsuitable for truly long-term applications. In other words, every isotope represents a different sacrifice: more power, more safety, or more time. You never get all three. To put those numbers into perspective, a few microwatts are enough to power a single autonomous sensor, measuring temperature, pressure, or radiation continuously for decades. Tens of microwatts can support ultra-low power medical implants, such as early-generation cardiac pacemakers or neurostimulators, where reliability matters more than performance. Atomic batteries don't replace usual batteries, they replace maintenance and are used where replacement is impossible. In the 1970s, nuclear-powered pacemakers were designed to operate for 20 to 30 years, at a time when conventional pacemakers' batteries often required replacement every 5 to 7 years. These devices used radioisotope power sources because reliability wasn't a convenience. It was a medical necessity. Some nuclear pacemakers were removed not because they failed, but because the patients outlived them. In several documented cases, the power source was still functioning after more than 2 decades of continuous operation. Imagine being told your medical implant will need surgery every 5 years, not because your body failed, but because the battery did. For some patients in the 1970s, atomic-powered pacemakers quietly changed that equation, not by making medicine more advanced, but by making it stop interrupting life. Atomic batteries didn't fail because they don't work. They failed for 3 reasons. First, power. Microwatts are perfect for sensors, useless for screens and motors. Second, economics. Atomic batteries are built for decades. Consumer electronics are built for replacement. And third, psychology and regulation. The word nuclear triggers fear, even when radiation levels are lower than background exposure. Technically brilliant, commercially impossible. Atomic batteries never disappeared. They moved into laboratories and niche industries. City Labs, founded by nuclear physicist Peter Gaboy, develops betavoltaic batteries for medical devices and remote sensors. In China, research teams have demonstrated Nickel 63 betavoltaic prototypes designed for long-term micropower applications. These are not consumer products. So what happens if an atomic battery is damaged? There is no explosion, no chain reaction, no meltdown. Betavoltaic batteries don't store energy, they generate it slowly. If damaged, power output drops. The system degrades. Beta radiation has extremely short range, often stopped by millimeters of materials. They are engineered so that when it does, nothing dramatic occurs. Lithium batteries are measured in cycles, atomic batteries are measured in decades. Atomic batteries work where nothing else survives, and that's exactly why you almost never hear about them. We live surrounded by devices designed to age quickly, replaced, discarded, forgotten. Atomic batteries prove something uncomfortable. Technology doesn't have to fail this fast. If this changed how you think about energy, don't scroll. Hit like so this video doesn't disappear. Subscribe if you want more real science, not hype. And tell me in the comments, which part surprised you the most?